So just going from the beginning, right? This is our end goal, just being able to solve like a regular roller coaster problem and figure out the force, right? But we started off talking, I should probably should have fixed this. The correlation between impulse, which we talked about in last unit, right? Impulse is the force happening over time. So like if I punch somebody real quick, it's a big force they feel in a short amount of time. Or if you have a car crash, right? That's a big force between two objects that you feel in a certain amount of time, right? But now when we talk about energy, we want to talk about the scalar form. We're talking about that work being done for a distance, right? Over, sorry, a force being over a certain amount of distance. So that same type of having a force, but just over a certain amount of distance, right? So that's where we see the parallels. But and then also work is parallel to the surface that it is. So that's why I have that cosine and the angle there too, right? So once we did that, this is really the most important part to really kind of bring it up with energy, right? So we do have that impulse is a force over time, which causes, remember, a change in momentum. And work is a force over some amount of distance that causes a change in energy. So impulse, change in momentum, those are similar. Now work is also equal to a change in energy. How does that come into play later on? We did all this where we basically just calculated work. And this is again, it's talking about the angles, right? But that last part, I want us to stay there, right? Now, when we start talking about work, right, we know work is pretty much a change of energy. So any change of energy, force done for a distance, right? That's what we talk about with work. Now, when we want to represent things as a rate, right, we do work over time, right? So we have work over time. So the rate at which I change my energy or the rate at which I do some type of work, we call that power. So that's when you have like your charger works at 20 watts. So this is how much energy per second, right? Energy per second. So that's our work power, right? So that's our power rating. We use that for all different types of appliances and understanding, like, when you have like your electricity bill, like how can you say like how much energy I'm using? We measure that in a rate versus time. So same thing, right? But if we break it down, right, this is where it starts to get to like kind of play on to things that we kind of know about, right? If we have power, right, we say it's work over time, right? That means that essentially the force over a certain amount of distance over time will be equal to power, right? Now, if I just shift my parentheses and move it over to where I have my distance over or displacement over time, right? We could then represent power as a form as force over velocity, right? So if you think about it in the packet, it has one example talking about like a football player, right? What type of football player would you want on your team? Would you want a skinny one or one that could generate a lot of force? Big, thick linebacker, right? But do you want that big, thick linebacker to be slow? You want to be fast. So that's why we just seen with the NFL draft, we got these big old linebackers, big old linemen who might be 300, 400 pounds, can do a whole bunch of bench presses, but they run between like a 4.5 and a 5.47, which is extremely fast for that much of a large person. But you don't want to just have a lot of force. You want to have a lot of force at a high velocity to generate a lot of energy over a short amount of time. So that's when we want to talk about with power rating, right? So now what it's talking about power, right? We talked about work. Work is the change of energy. Power is the rating to where we can rate and talk about how work changes over time, right? Now let's play around with some of these questions, right? Now this is more conceptual, right? So now we have our work rating, right? Power rating, right? Over to the right. Just remember that, right? During the powerhouse lab, Jack and Jill ran up the hill. Sound familiar? Jack is twice as massive as Jill, yet Jill ascended the same distance in half the time. Who did the most work or who delivered the most power? Now, this is not to think. This is really just to ask, to get some answers and input. So for the first one, this one could be more interactive, like being in the chat, right? Or you come off of mute and explain your answer. So for the first one, who do you think did the most work, Jack or Jill? Put it in the chat, and then I'll have somebody come off mute and answer.
Jack?
Go ahead. Say it again.
Would it be Jack and Jill since they both ran up the hill?
So you said Jack and Jill. So are you saying they both do the same amount of work?
Yeah,
Now, what's your explanation for that?
because they both ran up the hill.
They both run up the hill, go a little bit deeper.
Huh?
Give me a little bit more.
They both ran up the hill to go get to fetch the bucket of water.
Yes. Now, what about the hill? Concerning Jack or Jill.
I think Jack ran down.
So they both think about they going back up the hill, right? So
Okay.
as it says they're going back up the hill, right? Now, when we talk about work, right? Let me just help walk you down, right? Work relates to, hold on real quick. Let me make this easier.
Is your screen on still?
I just removed it. Hold on, give me 2 seconds. I'm gonna just add something to these slides real quick.
Can't see the slides. Let me log out and log back in.
No. I turned it off. You're fine. Hold on, I'm about to share again. Oh, that's why. Hold on real quick. There's an error. I should have did that one first. Give me a second. I made a mistake. That was supposed to be an easy one. All right. I wasn't supposed to do that one first. Go to this question, right? So I just said it really. Power is defined as what? The amount of work that is done, or the direction at which work is done, the angle at which work is on, the rate at which work is done. Remember we said earlier? Hold on. Power is what? Work over time. What does that sound like? Does that sound like over something? When we say over something, a rate, right? Now we come here. Which one are we going with? A, B, C, or D? D. So power is the rate at which work is done. Work also is the change of energy. So you could say power is the rate at which you change your energy. Kind of similar to how we talked about velocity, right? Velocity is the rate at which you change your position. Acceleration is the rate at which your position is changing. So look at like to make it that parallel, right? So remember that. Now when we talk about power, right? Two machines, right? They might do two identical jobs, right? Which will say like is lifting 10 passengers up 3 floors, right? So the same 10 passengers for each machine, right? 10 floors. Yet the machine have different power ratings, right? Explain how this can be. So we have two machines and they do the same job. Two machines do the same job. They're lifting 10 passengers up 3 floors, right? So let's think about this, right? Power is the force that you do a distance force that you do, well, sorry, power is the work over time, which could be the force that you do per distance over time. So how can these elevators do the same job, but yet have different power ratings? If one does it faster. So if one does it faster, what does that mean? Has more power, but in which way? Let's go back. The time is shorter, right? But remember that last one we did? If you represent the distance or displacement that you change over a certain amount of time, you could actually represent it in this velocity. So that force, right? What's a force that tells us how much how much the Earth is gravity is pulling on us? What's that force? What's the force that tells us how much gravity is pulling? That's our weight, right? So that's our weight, right? So you can calculate each 10 passengers, their weight is their force, right? So if it's the same 10 passengers, they're going to have the same weight, which means in both machines, they have the identical force. Now, for them to have a different power rating, we look at it right here, right? The time must be different because the distance is the same. So with the time being different, that means that they're going that distance in a shorter amount of time, which if we know that the displacement or this distance over time is equal to the speed or velocity. So that means that because it's a short amount of time, they're actually moving at a higher velocity. So for our explanation, power is the rate at which work is done. The two machines are doing the same amount of work, but doing the work at different rates. One machine might do the job very quickly, and the other one might do it very slowly. The machine that does the work at the least amount of time quickly is the most powerful. So like we just said, that time difference, right? So that even calculates to like your electricity bill, right? So if you're using up a lot of energy within the month, right? Then you're going to have a higher electricity bill than someone who doesn't use as much energy, right? It's still the same 30 days, but if you have a higher rating, then that's fine. Or you might use the same amount of energy that someone uses in a year in 30 days. So now your bill is really high. So if you have all these appliances on and you have all these things going on within this first 30 days, and you're going to have a higher bill because you used up someone's yearly supply of electricity that they would use in about 30 days. So that's where that example of that time, right? So we got another situation. So two physics students, Will and Ben, are in a weightlifting room, right? So now Will lifts the 100-pound barbell over his head 10 times in 1 minute. Ben lifts the 100-pound barbell over his head 10 times in 10 seconds. Which student does the most work and which student delivers the most power? So let's try and dissect this one, right? So first they ask about work, right? Let's take it by the definition of work. Work is the amount of change in energy, right? Or it's the amount of force that you do over a distance, right? Now, let's look at this, right? Will and Ben, right? Let's assume they're the same height, right? So if they're doing it over their head, right? Are their distances different or the same if they're the same height? The same. So if they just go over their head and they both the same height, they just going like this, just doing a nice little shoulder press, then they go in the same distance. So their distances are the same, right? And let's say the force, right? So the force, which we said earlier, with lifting like the passengers, right? The force will also in this situation be the weight, right? How much does the barbell weigh? Are they both using the same weight? So now we could say that the weight is consistent, right? So now the weight is consistent and the distance is consistent, right? So what is different? Also, how much? So when they're doing their force production, right? They're lifting it 100 pounds, but 10 times. Do they both do the same amount of reps? So they both do it 10 times, right? So what's different between the two? So who would have the most power? Say it louder. Ben. Why'd you say Ben? 10 seconds, which is faster, less time. So Ben has a higher power rating. But now when it comes to their work, is their work different or the same? Go ahead, debate. She says the same. She says different. You say same. You say different. Why do you say same? 100. Oh, that's your explanation, right? Why'd you say different? So in this one, what are they doing? Changing energy, right? So what is the weight that they're actually changing distance?
Regardless of their personal weight, it's the same amount of force.
And to keep it consistent, I just said assume that they're the same height so that the distance is the same. So now, do you still say it's different?
I would say that they did the same amount of work. Maybe I'm just looking based off the formula. Sum of forces over distance and sum of forces over distance. The only difference is the cosine of it.
Okay. Now, if you think about it, right? With the cosine is the angle to which they're doing because it's the angle, right? They're just going up, right? So for both situations. So now I'll take away that. The cosine, is there anything different? So they're doing the same amount of work. So do the same amount of work, but who has more power? Make sense with the explanation? The students are doing the same amount of tasks, thus the same work, yet Ben does his work at a higher rate. As such, Ben is most powerful. Higher rate, less time, faster, quicker. Now let's get to this Jack and Jill problem, right? So now I think we should get it. Also, are y'all hearing me online?
Yeah, it's perfect.
Okay, cool. So now let's get to this Jack and Jill problem, right? So using the definition of power, we want to explain the situation, right? So now we want to use the definition of power. And I didn't put work here. Hold on, give me 1 second. I'll change that real quick. Just so you're not confused. So during the powerhouse lab, Jack and Jill ran up the hill. Okay, so now we got that part, right? Pay attention to the words, right? Jack is twice as massive as Jill, yet Jill ascended the same distance in half the time. Who did the most work? Who did the most power?
Jill.
Who did what?
No. Jack, I mean, they both did the same amount of work, but she delivered the most power.
Okay, so you got, real quick, hold on. You put Jill and the same, right?
Yeah.
So Courtney said they do the same amount of work, but Jill has the most power. Anyone agree? I got Sean in person saying he doesn't agree. I'll come back to him anymore. But anybody agree? Want to say on the chat that they agree?
No, I said that they put in the most of they did the most amount of work because it's the rate at which the work is done. And then I said they delivered a different type of power because it's different over I mean it changes over time, but I said that she did the most amount of power because she used more energy, I mean more acceleration to get there faster. Even though he's bigger, she still used more energy. She had to use more energy, twice as much energy than him to get there in half the time faster, if that makes sense. Maybe I'm not saying it right, but it makes sense to me in my head.
Isn't the inverse true? He would have to use twice as much energy to travel the same distance twice as big.
Say that part one more time. Can anybody hear Sean?
No.
Isn't the vice versa also true that the person who is twice as big would also?
We can't hear him. He's too far back.
No, I got you. Okay, go ahead.
I was saying, doesn't it work vice versa? The person who is twice as big also has to exert twice the force to go the same distance.
Yeah, but
So I
she
would
got
say
there
that these
faster.
are the same force and the same power.
So now you're saying same force and same power.
No, I say no because she got there faster.
So you're saying no, Courtney, that they have the same amount of work and they have different amount of power, and you're saying Jill will have more power.
Yeah,
Correct.
because she got there in half the time.
Okay. And then Sean is saying the actual verse where he's saying who has more work.
I'd say they have the same work.
So Sean says they have the same work and same power. I see Lakshmi is saying, looking at me, saying something about to say something.
Whoever's faster has this power.
So you're agreeing with Courtney.
Uh,
So you agree with Courtney with the power rating, but you think that they have a different work.
we have to know how much work was done to find out the power.
Well, think about it. How much work would be what? The force per, look at the equation. First times the
This
distance. And let's even go back, right? So all this stuff, this change and everything, right? Even goes back to Newton's laws, right? A change in motion, a change in anything, right? Is generated by what? Force, right? So in this situation, right?
so the man will be more force because
Why?
he's bigger.
Because he's bigger, right? Because if you look on, I'll put it on the screen, right?
So there'll be work.
Remember what force is equal to?
The sum of force.
Change over time.
Force is equal to second law. Mass times acceleration, right? Now, specifically, if we talk about, stay with me, don't lose me, stay with me. The force we're talking about specifically is someone's weight, right? I'll put it on the screen. The force due to gravity, right? That's someone's mass times gravity, the acceleration due to gravity, right? So if I'm a person, right? And we say that right here, how their mass compare, right? How is Jack's mass compared to Jill's? So let's do Jack over here, right? So let's do FG for Jack. That means if we do it based off of Jill's math, let's say Jill, I need a trackpad. Let Jill equal her mass equals M, right? So if Jill's mass equals M, that means Jack's mass, because he's twice as massive, is 2M, right? So then his force or weight, force due to gravity will be 2mg, right? Whereas Jill's would just be mg. So what does that do in terms of their force, right? Jack's force would really be twice that of Jill's. So Jack has twice as much force as Jill, but they go the same distance. So now if Jack has basically, let's just say it, this is Jack, right? Jack is 2F times the distance, right? That's his work. Where Jill is F times the distance, right? Just her force, right? Just her regular force. That's her work. Essentially, Jack's work will be twice as much as Jill's, because he has to lift up his more massive body twice as much to go that distance, right? Does that make sense?
Oh, so the power will be the same.
Now, why do we say, hold on, do we get the work part, right? So the work is Jack would do more. He is more massive, so it's going to take him twice as much energy to go that same amount of distance. But now we're going back into, now we know that Jack does twice the amount of work, right? Compared to Jill. But we also know that Jack does that work in a certain amount of time, right? Jill does that same amount of work, sorry, not same amount of work, goes that same distance in half the time. So if I rewrite these, right, down here, right, you have their individual power ratings, right? Because power is basically your work over time. So now we have Jack's power rating, which is twice as much the work over a certain amount of time, while Jill's power rating is half that amount of work times, but she did it in half the time. And I'll actually rewrite it, because if you come over here, right, this really, because this is a fraction on the bottom, it ends up becoming 2 WT. So really this ends up down here being this. And why is that? Just real quick, if I divide by a fraction, right, let's say I have 2.
So it's basically canceling each other.
Exactly. If I divide by a fraction, 1/2, what you really do is multiply by the reciprocal. So that'd be like 2 times 2/1. The reciprocal is a flip.
Or the inverse of multiply.
Exactly. So dividing by a half is the same as multiplying by 2. But what does that mean? That means now that instead of dividing by half the time, we're really multiplying by 2, to where now they have what with the power rating? The same. So now we see that they have the same power rating, because even though Jill is less massive, she covered the same amount of distance in half the time. So now they have the same power rating. So Jack is more massive, but he's moving and covering that distance slower than Jill, who's less massive and covering that distance at a faster rate.
So it's only faster equals more powerful if the work is.
Say it one more time.
Because I was thinking faster means more powerful, but that's not always true.
So
Faster means more force or weight.
so think about it. Remember how we went
Because the other problem we said, the faster person was more powerful.
come back to where are we at? Here. So now we have, hold on, let me make sure I erase this so it's not in the way. That bottom one, right? This is where we're really talking about in this last one, right? Because you are doing a force, right? How is that force being done? Especially here, right? So this is where the rate part comes in. Like, yes, we write it as work over time, right? But I think this power times force times velocity is actually important, because how you move that force really determines the rate. So like Jill in this example, right? She weighs less, but she's moving faster. How much?
Twice,
Twice as fast.
but she weighs half his weight.
Half his weight. So when you think about it, those two cancel out. Because it's that she just weighs half it. Now, if it was a different type of measure of force, like it was just astronomical, it was the Earth or something like that compared to Jill, of course they wouldn't be the same.
So
But-
this one's easy because it's a 1-to-1 or 2-to-1 ratio, whatever it is.
Exactly.
The ratio is so.
Do I have one like that? I might have one like that. No, I don't. But if it wasn't, you would just have to calculate it. But these are not supposed to be difficult to, are you still seeing my screen? Yeah, these are not supposed to be difficult to get you to that deep where you start looking at it. These are supposed to just kind of give you like an idea of it. And then I show you how to calculate the power and stuff. And then when we get into the relationships, then we can get into that. Oh, what if it's this? What if it was that? Like this one, right? The two students are not doing the same task. Their work is not the same. Jack must lift twice the mass as Jill. So Jack does twice the work. And because Jill does 1/2 the work in half the time, then they end up having the same work ratio, because once you start doing the math, it ends up being the same. Also, power is measured in works. And sorry, not works. Power is measured in watts. I think I said that. So like how you have like your charger. Yeah, power, watts. Change the energy over time, watts. So that's what you have like your charger, watts. Joules is energy, yes. There we go. See? We want to talk about energy in a second. All right. So for this one, real quick, how will we calculate the power rating of this motor, right? So we have an elevator, it lifts
715 kilograms to the height of the fourth floor of an office building.
let's say it has about 11 meters, right?
Constant speed, 9.35 seconds. Power rating. The force, we would have to calculate we would have to convert the kg into force. So is that
Walk me through it. Yes, you're doing good. So now you said our force, you said convert the kg in force. So what are we really doing? We're finding the what of the object, the weight of the object, right? So we know that the weight of the object is equal to the mass times gravity. What's the mass?
Excuse me, I have a question.
Go ahead.
I was trying to print the screen from the last slide because I didn't hear the last answer.
mass is 750.
Hold on. This one.
Oh, okay. Thank you.
Oh. All right, one more time. Oh, I just heard this now. Oh, I did get the answer. My bad. All right. Now we're going here, right? So now we know how to calculate the weight, right? Doing this, right? So what's the mass?
It's 750.
And then we have to multiply that by gravity, which is what? The 9.8, right? So we just do 715 times 9.8. Real quick, anybody got that? 7.5 times 9.8. 715 times 9.8.
Where did the 9.8 come from?
What is the acceleration due to gravity?
Oh,
750.
7,007. All right. So now that's our newtons, right? This is our total force. Now, what do we do with this force? So now we want to use this force for our, let's say, we could just go straight to, actually, I'll do it this way. Let's find our work first, right? Force times the distance. What is our force? 7,007 newtons. And do we have a distance? 11 meters above the ground. So now let's calculate and find our work. So what's 7,007 times 11 meters? So our total work is 77,7700.
7707.
077. So 77,077 meters. Sorry, 77,077 joules. Joules, because that's a unit, right? So this is the total work being done, right? We elevator lifts this amount of force up, this weight, for 11 meters. This is the amount of energy that's being done, right? Now the last thing we have to do is figure out the rate at which that energy is being done, right?
Divided by 9.357.
So we want to divide this energy being done, this work, by the time, right? So we're going to take that 77077 and then divide it by the time that was given to us, which is what? 9.35, and you get what? I'll put my power rating up here. 8244.
Yes. 8244.
So 8,244 watts. That's our power rating. Let's see if we got that. Yep. 8,243.52. Same thing. So that's our power rating, right? How do we start off? We found our mass of the, we found our weight of the object by taking the mass times the acceleration due to gravity. That's our total force. And since we're elevating, we're lifting up that force up. We want to multiply that force by the distance that we're lifting that force up, which is 11 meters. So that's how we got the 77,000 and 77 joules, right? Now, how much are we lifting that force up for that distance per time, right? For that, to get that rate. So that's the power. So we want to take that energy, that's 77,000, and now we want to divide that by the time it takes to do that to get our power rate, which is 9.35. And once we get that, we have a power rating of 8,244 watts. So that 8,244 watts is telling us how much energy we're using per time, per second, to lift up this weight when it's elevating. Now that's the math, but does it logically make sense? What seems the difference between work and power? You don't got to come off mute, but thumbs up will be appreciated. Just know if I'm not losing anybody.
No, I just need to do another problem. This one's easier than the other one.
Okay, cool. All right. So I wanted those to be easy to kind of, you understand how work is being. I remember to erase this, sorry. So understand how work is being done, right? Then when we understand work, we can do power rating, right? But let's really focus on energy, right? We talked about just energy in general being changed, right? But we didn't talk about any specific types of energy. There's all different forms of energy, right? So right now we want to focus on two specific types of energy just to get us our feet wet and understanding how energy works, right? So remember, work is a change of energy. So like say delta E, right? Change of energy, right? If we go deeper, right, there's different types of energy. The first one we want to talk about is kinetic energy. So that's the energy of motion, right? So that's literally, like I said, like if you think about the bank account example, that's the checking account, right? You have money transaction always between your checking account going in and out, in and out, in and out to transfer, right? You move it from here and here and here. Just think about emotion, right? It has its own equation, right? Where the kinetic energy in a system, right, is equal to 1/2 times the mass of whatever object that is times its velocity squared. 1/2 times the mass times its velocity squared. Then we have another one, which is potential energy. Some people like to call it as what you do when you store something on the shelf, right? You kind of save it up there, but I like the bank account example still. So if kinetic energy is like our checkers account, you could say potential energy is like our savings account. I save this energy up here, right? And I don't transfer unless I'm ready to withdraw or something like that. So I just save it up there and I just have it just sitting up there. So we call that potential energy is equal to something's object's mass times its acceleration due to gravity and its height. That's where you get the shelf analogy. Like I'm putting something on a shelf, right? So if I have I say my desk is 0, right? And I lift my laptop up, I just gave it some potential energy. Technically, because we're on what, the 3rd floor, if the ground was our 0 outside, we all have potential energy to keep us above the ground. Now, when we do is like, if we come up from like the top of the stairs and we go downstairs, now we're transferring that potential energy into kinetic energy so that we can move, right? And we usually do a lot of that back and forth a lot of times when it comes to different objects and different like scenarios, right? So we represent that back and forth between kinetic and potential energy as mechanical energy, right? So the energy of an object due to its motion or its position is called its mechanical energy. And so we want to see that sometimes that energy fluctuates in the system. What's one example when you see a potential energy and kinetic energy shift a lot?
Like a spring
spring or a slinky. One that's I'm kind of like forcing the answer because it's related to our problem, and also it's very easy for me to explain. You go to the amusement park and you ride,
The slingshot.
which is a roller coaster. Perfect. There we go. So think about a roller coaster, right? You're moving, then you go up. You're moving, then you go up. If you're at the top of the roller coaster, and when it comes to that stop, right, before you go down, you know, like if you're going to Superman, like you go all the way up to the top, and then you stop at the top, you're fully at potential energy. Then when you start coming down, you're at potential, and you have some kinetic energy because you're moving, potential and kinetic energy. Now let's say you get to the very bottom, right? You're moving, but you don't have as much potential energy because you're at the zero. So like that fluctuation between kinetic and potential energy, we call that mechanical energy. Your total system energy is mechanical energy with that, right? And we just watch it like change over time. So remember that mechanical energy is your kinetic and potential energy together.
And is that the entire system, or could that be a specific point in time?
The specific point in time of that system. The specific point in time of that system. So like top of the roller coaster, more potential energy. Bottom of the roller coaster, more.
So there's never an instance where it's like calculate the mechanical energy of an object for like this minute
It's like at this point.
at this point. Okay, so it's
Yeah.
always at a
Because think
specific
about, wait, what'd you just say? At this minute, right? That's a what now? When you say at this minute, right? For this minute, that's a what? Time, which is change of energy over, which is now a rate, which is now the rate of energy changing, which is
rate on power.
power. So now you just changed from just talking about energy to now how the energy is changing over time. So what you got to rate. That answer your question?
Yes.
All right. This one, not too much math, still conceptual, right? So let's go through each of these, right? Come off mute, or because honestly, you come off mute or you can just put it in the chat. Just be interactive with it, right? So we want to read each situation, right? And determine if it deals with kinetic energy, potential energy, or both. So let's say if an object is at rest, right? It clearly does not possess this form of energy. If an object is at rest, it doesn't have this form of energy. You say potential? Why do you say potential?
At rest.
Say that one more time. If an object is rest, its velocity is equal to 0. And by the definition of kinetic energy, what does it require for it to be not 0? I don't know if that's the right way to ask it. By the definition of kinetic energy, what two components does it require? Mass and velocity, right? So if an object is rest, you just said it one more time, the object's velocity is equal to 0. So therefore, if velocity is 0 in a kinetic energy equation, what about the kinetic energy? It should be equal to what too as well? 0. Now potential energy, does it require velocity? No. So you can have potential energy while you're at rest. Just
I
like
don't
the sitting on the
understand the
shelf
first one.
example.
You was talking so fast. Hold on. What did you say about the first one?
It's potential.
The first one, right? So if an object is at rest, what does that mean when an object is at rest?
That means it has potential energy.
Hold on, don't just jump to potential energy. If an object is at rest, what does that mean?
It's no momentum, it's 0.
What's 0?
I don't know. There's so much going on in my
You
brain.
do?
I
You
can't
do?
even think what to call it.
Go back to all the way to unit 1. When an object is at rest, what does
Equilibrium
that mean?
is at 0. Acceleration is at 0.
If acceleration is at 0 because the object is at rest, what does that mean? What else is at 0?
The velocity.
The velocity is at 0 when the object is at rest, right? So now if the object is at rest, right, and it has a velocity of 0, which form of energy, based off of the equations that we see to the right, contains velocity?
The kinetic energy.
Kinetic energy, right? So what does kinetic energy need to be present? It needs a what?
Have
Go ahead.
motion.
Have motion. So for it to have motion, it needs a what?
Move.
And it needs what to move? A
Object.
object that has to have a what? Look at the equation.
Force.
Not force. Look at the equation.
Mass.
And a
Velocity.
velocity. So if an object's at rest, does it have a velocity that's more than zero?
No.
No. So therefore, its kinetic energy's velocity will also be
Zero.
zero. So if it
And
has a
that's where I
velocity
get
of zero,
lost right there. That's exactly where I get lost. I don't understand that.
stay right there. So if the velocity is equal to zero, right? You got that part, right?
Yeah.
The velocity is equal to zero. So if I was to do this equation, this is just mathematical, right? For the velocity is equal to zero. So instead of v, I will put in what instead of v? I will put what number?
Zero squared.
Yes. What is zero squared?
Zero.
Zero. So then that means anything times zero is also what?
Zero.
Zero. So everything in that equation will be equal to
Zero.
zero. So what does that mean logically? That means if I have zero velocity or no velocity is present, does that mean I have any kinetic energy?
No.
No. And what does that mean in the first statement, right? That brings it back to if an object is at rest, go ahead.
It's at rest, right?
So if it's at rest, that means it has a velocity of
Zero.
zero. So if it has a velocity of zero, then can it have any kinetic energy?
Huh? Could you say that last part?
If it has a velocity of zero, can it have kinetic energy?
No.
No. So with this statement, right, what form of energy does it not possess then if an object is at rest? The answer would be, it's a weird way to say it, but what energy is not present because the object is at rest? Yes.
Motion.
Which energy between kinetic and potential? Does it not have?
Gravity.
Between kinetic and potential, does it not have?
Kinetic.
There we go. So that's the first one. That makes sense now? You good?
Yeah. So basically, the first one, we put K. We put neither.
No. You put kinetic because it doesn't have kinetic. It's weird how they worded that first one, but they want to know which one is not present, which would be kinetic energy because the velocity is equal to zero.
It's the way they worded the whole question that got me confused, and it's weird.
Yes. So let's just go to the second one, right? So what forms of energy depend on the object's mass and height? Look at the equations to the right. Which one depend on the object's mass and height? Potential energy, right? Mass and height. Now let's think about it, right? I'm storing something on the shelf. How much it weighs would tell me how much energy it takes. Sorry, its mass would tell me how much energy it takes to store something on the shelf. So I have a lot of mass. It would take a lot for me to keep me above ground, right? Compared to like Seth, I believe I weigh more than Seth, to where like it would take him less mass or probably less energy to keep him above ground compared to me if we were doing like the same height. But for this one, potential energy depends upon the mass and height of the object. Now, this one, since we just did potential energy, the energy of an object possesses due to its motion. Which one is that? Kinetic or potential? Or both?
Kinetic.
Kinetic, right? Good. So kinetic, you said earlier, motion. Storing something on the shelf, mass and height, potential energy. Now, coming to this one, right? Let's do like this. K, P, K. Now for this next one, right? The amount of is expressed using the unit joules, right? So which form of energy has joules as a unit? Kinetic, potential, or both? Both, right? They're both forms of energy, so they both use the same unit. So kinetic and potential energy are both use joules. So now we keep it going, right? Now, the energy stored in an object due to its position or height, is that kinetic energy or potential energy? Stored due to its position or height. Remember the word, the language, right? Which one did I say is like a savings account? Potential or kinetic?
Potential is like the same.
Potential is like the saving account because you do what with it? You store it, save it for a rainy day, right? So if we look at this one, right? The energy stored in an object due to its position or height, which one is that? Potential or kinetic? Or both? Potential, right? So that one is potential. You see the word store, think about potential, right? Storing on the shelf or storing in the bank account, saving it for a rainy day. Now, so now this one, let's think about it, kind of relates to the previous one. The amount depends on the arbitrarily assigned zero level. So we could assign different zero levels, right? We could say the third floor is what we're considering the zero level, or we could look at the ground as zero level, like outside the ground. But if we're talking about where the zero level is, we're talking about a height difference. If we're talking about a height difference, which form of energy are we using? Potential or kinetic? Potential.
Matters about the height.
Good, potential. So for both of these, last one, 5 and 6, is P. I'm trying to write it in. So then we go to the next one, right? Which one depends upon an object's mass and object speed, right? So let me go to the ones to the right, right? We talked about it. Potential is store energy in motion, right? But when we have to transfer, right? Remember, we're moving from the savings account to our checking account. So we're moving it because we have that transaction back and forth, right? We're moving from I'm buying something at the store, I'm maybe putting some money and depositing it, like I'm doing all these different transactions, right? So that's motion, right? So when we have an object in this movie, right, we're concerned with two things. Its mass and its what?
Talking about for the potential.
If an object is moving, we're concerned with its what?
Concerned with its mass, velocity.
Velocity, speed, right? So which energy form would that be?
Kinetic.
Kinetic, good. Last one, right? If an object is at rest on the ground, zero height, it clearly does not possess this form of energy. Think kinetic, potential, or both. Say it louder. Why you say both, Seth? No velocity because it's what? At rest. So in this scenario right here, we have no height. So that because it's at zero, so that's no potential energy, and it's at rest. So that means it's no velocity.
What does that mean? So two-dimensional objects.
You're complicating it right there. What happens when you go on a roller coaster at the beginning?
Oh, okay.
Yes, that's why I say use the roller coaster. Right before the roller coaster starts, we right at the gate. Before we go any further, that's literally when we have no kinetic, or you could say it doesn't have both. There's no kinetic, no potential energy at that moment. You could say it's a zero level, and we're not moving. So we have those right there. Let me see real quick. Hold on. All right. Come back in like 5 minutes at 7:10. It's like 6 minutes. So take a quick break and come back. See you later. I'll pause the recording real quick too.